Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the Windows operating system components that are mainly layered with three architecture. One is the hardware abstraction layer, one is the execution layer, and another is the kernel level layer, which will interact upon these things between many of the services and subsystem performances. So we will discuss these sections in earlier and elaboratively today. So the main layers that is provided by a Windows system is provided with HAL or the hardware abstraction layer, the kernel and the executive layer. These three layers just interact between themselves to give us the most important and proficient system as Windows operating system. Now, this HAL kernel as well as the executive, three of the layers provide some of the subsystems and the system services that is performed by the operating system. The executive layers provided with two of these other layers. One is the environmental subsystem, which provides us defining different types of operating system types, and another is this protection system types, which gives us the security features of the particular operating system. Now these interfaces can simply interact between these modules very seamlessly, so that can we perform all the subsystem and services in our accessed manner by the user and kernel level processes. So we will first describe the HAL layer. Before that, we will know that how the system components looks from outer view or an user view of the system. So it is the system components of Windows. Here we can see that the main three layers are the HAL, the kernel, and this particular executive subsystems. So the HAL is the layer now we will describe. Now this HAL differences between the hardware chipset of the particular upper level operating system. Say you can see that here is a difference between this hardware platform and this all the operating system above, that is the user mode as well as the kernel mode, and it is differentiated by this HAL. So this hardware abstraction layer just communicate with this particular executive, the device drivers, as well as the particular virtual manager. So the hardware abstraction layer gives us an idea about what is the device driver controller, which will in turn return the device driver handles to the particular hardware and gives it information about the available devices within the system, and all the executive objects that should be run by this particular kernel mode, which is interfaced with the hardware by this HAL. The next mode, as we can see, is the kernel mode. This kernel is responsible for many of the objects and it will be handled by directly the operating system. Generally, the kernel maintains a system entities that should be handled only by the operating system is known as object, and each object is of an instance type which is then instantiated by the kernel object. So the kernel object can perform any of the following tasks. First, we need about this kernel object that it is dispatched by the kernel dispatcher. So the kernel dispatcher first dispatch the object that are ready to execute, and after that the objects are used to perform the system subsystem functions as well as all the service routines that are provided by the operating system. It also provides the thread scheduling functionality. As we know that the process are divided into threads and the thread should be scheduled upon the preemption of thread and empty process of thread, and other than that the thread arrives when a high priority thread is running. So in these cases the thread should be scheduled. So before going to thread scheduling, we should know that what are the states that are associated with thread. The threads are generally ready, standby, terminated, aborted, modified, and exempted. So the ready state means that the thread is now waiting to be run. When we are calling that standby, that means the thread is already in the CPU, is the next thread to be run. And this waiting state tells us that the thread is waiting because it is waiting for another thread to complete its action. Next is the preemption. Whenever a thread is preempted or waiting for a resource to be occupied by another thread, then it is in the preempted thread. And after that, the terminated thread tells us that the thread has completed its action either by abnormal or other by normal termination. So these are the thread states that are associated with thread, and according to this thread state, we can choose the thread to be terminated, preempted, or executed. So when the thread is in running state, we can say that the thread are actually executing in the CPU's memory. So thread running is directly responsible for the process that is created for that particular thread. So the thread can share the process's memory or the master thread that is actually the creator of the particular thread. So in this way, the threads can be run by the process itself and allocated CPU memory by the kernel dispatcher, which in turn gives the CPU process to the thread to execute on that particular task. Now the scheduling priority gives us when a high priority thread arrives and a low priority thread is interrupting, then it will be preempted by the high priority thread, and now the high priority thread will run on the CPU on behalf of this low priority thread. And if there is no thread that is free or available to run in the CPU, then a special thread that is a kernel threader known as an idle thread is run by the kernel dispatcher. This idle thread is always given the highest priority because it contains the operating system tasks. Now whenever a thread is interrupted, the interrupt is done by queuing the thread into an interrupt list, and it is done by an DPC or deferred procedure call. Deferred procedure call then just stops an abnormal interruption, sends it back to the operating system kernel to decide that the thread will again be run or not. So that means we are deferring the interrupt. For that, the process is now executing on such thread, and the process thread which is now executing and waiting for the thread to be run has to wait until and unless the interrupt has been solved by the kernel dispatcher. So the implementation of these threads and this kernel object is done by an object of instance type, and the object can be handled directly by the kernel to execute any task that it wants to perform. So there are generally kernel objects as well as user objects specified in the kernel operating system module. So the objects are as follows. An event object is an object that is used to notify that an event has occurred. The notification event signals all the objects that are waiting for a particular process, and the particular signaling process object signals that a particular thread is now executing and it has been interrupted or terminated its service. Next is the mutant object. Mutant objects provide the mutual exclusion between the user mode object and the kernel mode object. Next is the Mutex Object. Mutex Object provides exclusively the mutual exclusion between two kernel mode objects, and no user mode object is inferred here. The next type of object is a semaphore object. The semaphore object is to control the process execution inside a shared memory where another process is waiting for the particular shared resources to get accepted. Next is the timer object. Timer object is used as a timestamp protocol to define a process or a thread that it is running out of time or that an interrupt has occurred. Now the process has to be terminated or put into the waiting state until and unless the timer is again free. So in these objects, the object list, the kernel performs all this performance executively. So the object is performed by a special function called a handle. When a handle returns to the particular object, then we can say that the object is being called by a particular event. Then the event handler returns the handle to the application to specify that the object is now available and the application can execute on that particular object. After the application has performed the performance on that particular object, then it again returns the handle to the kernel to accommodate and identify that the application has stopped and now been terminated successfully. The next kernel mode activities is the APC and DPC, that is the asynchronous procedure call and the deferred procedure call. Deferred procedure call we have already described that it just abort or waits for an interrupt to occur by the deferring this queue in this dispatch queue of the threads that are running executively. And if there is a kernel mode object, then its execution is never preempted and the kernel thread can be run in that particular mode infinitely until and unless it has stopped validatedly and voluntarily to other user mode objects that can perform on the user space of the kernel mode object. But in asynchronous procedure call, it breaks into an execution thread and calls the remote procedure for executing that kernel mode thread has terminated abnormally, and now the operating system has occurred with some fatal error. So it traps it back to the operating system about that type of interrupt has occurred, and it now be preempted with some other processes either by a kernel or by a user mode process. The next service that is handled is the exception and the interrupts that can be handled by the kernel. So the exceptions and interrupt that are most general and specific and can be handled by the kernel are integer division by 0, floating point division by 0, integer overflow, floating point overflow, the debugger single step, the debugger multiple step, all the privilege instructions, illegal attempt to the access memory, and virtual address memory management, exception and all. So these are the general and also specific exceptions and interrupts that are handled by the particular kernel. When these interrupts such occur, first the ISR or the interrupt service routine get called. And after the ISR has provided the mutual exclusion and the particular interrupt services, then the only specific interrupts are serviced on behalf of the kernel. So the exception dispatcher dispatch the exceptions according to their priority. Say for the integer division priority is lower than an illegal access of attempting a memory area will be higher priority. So the exception dispatcher will dispatch these exception objects on behalf of the kernel to tell the operating system trap about that error and to correct and possibly modify the error. And there is an interrupt table which contains all the interrupt levels according to that to all the functions that are to be performed on that interrupt levels. So this interrupt table is maintained by both Win32 and Win64 as an application modification to the Win32 and AMD 64 application. The next type is the switching between the user mode and kernel mode processes. As we know, there are two types of thread. One is K thread, that is a kernel thread, and the user thread or the U thread. So the switching between these processes threads happen exclusively, it is dependent on the kernel, and the kernel decides that when it will preempt its execution to let an user process run on that user address space, are not allowed to execute any of the privilege instructions, and that can be only executed by that kernel thread. Whenever a user thread goes beyond its exception and then want to perform that particular privilege instruction, then it is said that the trapping back order to operating system and tells the kernel thread to take the necessary actions. So all the kernel threads here can be performed and transferred to this HAL interactions by executing that particular options. Now we will see that the executive mode, which will contain a different set of objects, and the executive mode will contain that the subsystem of the user mode, that is a Win32 subsystem, which has got a protection part as we have defined, that provides the security features, security databases, as well as different types of operating system inside it, as well as all the virtual distributed manager, say Win18, MS-DOS, POSIX, MS-DOS, POSIX VDM. So this user mode is generally specified by this kernel and the kernel specifies by this HAL. So in this way we can interact it by the hardware with the device drivers to specify the actual device drivers that the device controller now in active use, and it should use the device drivers to use the registers within that particular hardware. And the hardware components in turn executed the system software components which will be in the executive mode or executive layer. So now we will describe each of the executive layer objects in details. The first type of executive services is the object manager or OM. This object manager handles all aspects that is regarding an object. An object is essentially an instance of a template class, which is the object classes for the particular Windows system, say Win32 systems. So every object, the object we have described that the mutex, mutant, kernel object, thread object, dispatcher object are handled by this object manager. First, the object dispatcher dispatches the particular object associated with each task, and then in turn it provides that handles to the application indicating that the integer pointer to that particular object. Now there is a handle table which handles all the index pointer of that particular handle associated with that task to the application. Whenever an application is given a particular object, then a specific handle entry is made in the handle table to specify that the handle is operating on that particular application regarding that object. So essentially each object should be an object type, as we have already told, and the object type should be specified and defined only by the kernel, can only be used by the user. So the user cannot define but use the particular objects. So the object is residing at a disk position. So an application who want to open that object need to first get to the file location that is containing the object. After getting the address of the particular file location, then it searches for the entire directory. After finding that object, it returns the handles to the application which contains the information about the object. And after the application gets the object, it performs on it and again sends back the handle of the modified object to the prescribed location where the object was residing originally. So in this way, Object Manager handles all the aspects of objects very crucially, also seamlessly. Next, we will discuss about the Virtual Manager, which in turn takes care of mapping of the virtual memory to the physical address space of that particular object. Now, when the virtual memory takes care of the virtual memory to physical address mapping, it takes care of the demand paging and all the paging aspects of a particular memory reference area. So in Windows 32 system, it supports 8 KB and 1 MB pages for Win32, 4 MB pages for an AMD 64 and 2 MB pages for an IA64 subsystems. So this page tables is kept in the registers as the virtual memory is greater than the physical memory. And the register in turns to that particular session pages or the page tables that in turns contain the actual offsets of the pages. So whenever we are talking about these page tables, we can say that the page table has the page number and the page offset, as we have already told in the staging section, that will be indexed to get a page in the actual physical memory area. Now the self map maps the actual page table to the page offset. There are two types of space. One is hyperspace, thus contains the particular kernel pages, and a session space which contains a page's information about a particular session and gets changed and updated at every session which starts and ends. Now the virtual manager interns the pages, the maps from this virtual space to the physical space by two-step process. First is reverses on the pages, which is then brought into the virtual address space. Then it commits the allocation of the frames by just getting that confirmation that the pages are already being mapped to the physical address space. So in this way, we can map that virtual address space to the physical address space by these abortions and reverses and commits of that operation. Now we can talk about sharing of memory in the virtual memory by demand paging, which is created by a section object. So whenever a memory is referenced for a shared one, then it is referenced as a section object, and the physical address of the section object is then mapped to hundreds of references of the physical addresses, which can be considered as a collection of view. So whenever a memory is referenced, that the view is found that whichever the address that the particular process is shared about that views. So in this way, section objects are used. Now the virtual memory also gives the protection to the pages by two mechanisms. One is a no access page, another is a copy on write mechanism. With no access page, if there is any paging mechanism that want to access this page, so it will trap and back to the operating system to tell us that an no access page is tried to accessed. So the no access page is often used by the kernel to get some system dependent information which is not meant for page replaced and modified. The copy on write mechanism is used when two or more processes want to share an independent copy of the particular object. So first, a copy of this shared object is then shared in a shared memory area. Now after that, if any of the process want to modify that particular copy, then they will be given an independent and another copy of that particular object, which can be modified by only that process and will not be visible by the other process. So that the copy on write mechanism ensures that the copy will be given to a particular process's memory area if and only if the process want to modify it. Other than that, if you want to read the shared data, then it can do it by reading the virtual address space. Now there are many types of pages that can be provided by the virtual address. These are free pages, which can be allocated for the page replacement, zeroed pages which are now freed but before that it is zeroed, that means emptied out contents for the page replacement. Standby pages which are in the memory area but not yet has been written to the disk because they are already stored into the memory area. Modified pages that are written to the disk and has modified its contents, and also the terminated pages which are actually being terminated and replaced by the page replacement algorithms. And there are one more pages that is executing, that is being done executing on that particular active working set of information of the current process. And the last type of page we will be discussed is the waiting page, that is waiting from the disk coming to the actual memory area. So the paging scheme in this Win32 and AMD64 application is as follows. There are 32 bits to apply this particular paging scheme, where we can say the first two bits are containing the PTR, or it is containing the page table record. Actually, it is the index for the page table indexing, that is the page directory table. So this page directory table in turn that indexes for the page directories that will contain the indexes for the page table entries. So the next 9 bits contain the page table entries of that particular paging scheme. So this page directory entries will turn contains the page table entries, and this is generally 512 in numbers of 8-bit size. So this 512 page directory entries will contain 512 page table entries in the next 9 bits. And the page table entries will in turn points to the actual pages that is mapped to the physical address space, and the next 12 bits will give us the offset or the actual addresses of the physical space of the particular pages. The next type of Win32 system or the executive mode is the process manager. So this process manager takes care of all the process related ops, as the processes can be collected together to make a job object. Now the Win32 system supports the system calls that it create process for creating a process, terminating process for terminating a process, creating subs processes by spawning it using the fork system call, and then wait for the object using the wait for single object and wait for multiple object system call. The next type of the executive method that will be used is the PNP or the plug and play manager. This plug and play manager takes care of the hardware changes that has been done for the peripheral devices to get attached to the particular peripheral devices. So after the peripheral devices, if attached to operating system or the machine, then the operating system must be capable of the changes in the device drivers that is made by these peripheral devices and act accordingly of that particular device driver requirements. So the plug and play manager takes care of it and defines all the device driver instructions along with the device controller, which in turn places the registers to place that what peripheral device will work in what way. The next is the power manager, which is a part of the plug and play manager. It generally uses the machine's environment very efficiently in an energy efficient way. So it provides that the protect modes in the Windows supports is the sleep and hibernation. So other than shutting down the system, it can be put the Windows system in a sleep mode that goes that other than shutting down, it puts it while the hibernation is there so that the system can run below but the power is kept off. So the main difference of hibernation and sleep with the shutdown is, with the shutdown, if the power goes on, then all the system services and performances will be lost. But in hibernation on sleep mode, all the system services will be kept running on the background, but the power gets switched off and the active processes that are running or displaying in the screen will be off for the time being on the system is being put in the hibernation mode. The next type of manager that is provided by an executive is an IO manager. IO manager takes care of this caching manager, which in turn is related with this particular kernel memory and the actual den memory or the disk area. And the IO manager is responsible for the file systems and the device drivers which turns by the device controllers by placing the registers into the device driver, gets the contents of the device drivers on the registers, operate on it, and again back to the device controller, which will get back to the kernel or the operating system to tell that the performance of the IO has been done. So inside the file system now we will see that how the IO is performed. And along with the cache manager, the IO manager always takes care of the device controllers, that is the graphic device drivers or any other devices that can be attached as files. So the IO manager reacts with this file system and the disk driver with a non-cached IO. So any performance that done between this file system and this disk driver is then non-cached. But the file system when reacts with the cache manager, that is all about the cached IO that it will be performed. Now the cached IO will be the performance of the cache manager which will take care of the caching of the data. Now the virtual manager will reacts with the file system when there is page fault and paging should be done on the page replacement basis. And the virtual manager also get cached of the data for this virtual machine to the actual physical memory address space. So the performance is data copied between these two of this manager. Now when the process reacts with the IO manager, it is doing this actual IO processes. Now in this way, this cached IO, non-cached IO, page fault and data copy are related within an IO manager. Next we will come back to our last executive object, that is the SRM or Security Reference Monitor. The Security Reference Monitor takes care of all the aspects of security references that has been done to the object by audit checking the object and placing into an object table or security referencing the actual monitor which will monitors the object usage and access to the object, the processes, access control, access rights for accessing the object in a particular mode. So it will then define and checks that the process will be allowed to access an object or not, and if the object is in the domain for that particular process. The last relation of this executive and this HAL and kernel is the registry, that are the internal tables that contained in that kernel operating system is called the hives, and the hives are controlled by the registry. So registry is an essential interaction between the kernel and this particular executive bodies so that they can be controlled that the hives or the registries are performed only in the kernel mode, not in the user mode. And this registry will support the booting, that is the self-power on test, which will get operating system kernel loaded into the main memory, starts its execution from the beginning of the address space that was decided to load on that particular kernel. So that are all the system components for a Windows operating system. Stay tuned with Ekeeda, subscribe to Ekeeda.